All right, welcome everyone to this video. In this video, we're going to take a look at dnSpy, or focus more prominently on dnSpyEx, which is a fork of dnSpy, and I'll get into the details in just a minute. And we're going to use a Formbook sample, .NET sample, in order to really, as the motivation to explore the use of this tool. Won't get into all of the details. This is really just meant as sort of a primer to get you started using, again, real-world malware. So before we get too far, it's worth pointing out that the original project, the original tool, dnSpy, has now been archived and hasn't been maintained for a couple years. The last release, in fact, as you can see here on the GitHub page, was December of 2020. Recently, though, someone has decided to fork, and there's many forks, but this seems to become really emerging as one of the more prominent forks of the dnSpy project, called dnSpyEx. So this is actually the version that I'll be using in this demonstration, and you can go to their GitHub page and check out the binaries, the release binaries, if you'd like to download this to get those executables. You may be working with a distribution such as the Flare VM that installs dnSpy for you. I'm not sure what version offhand is installed there, so you might want to just check the information. If you're looking for something, again, that's a little more up to date, then this fork, dnSpyEx, is a great resource to go to. So again, be using this one here in today's demonstration. Now, as for the sample, I'm going to be looking at this particular sample. There you can see the hashes. I'll add the link to the to this entry on the Malware Bazaar in the video description. You'll notice that it's already been tagged via the signature as Formbook. Now, one of the benefits of uploading a sample directly to a platform such as Malware Bazaar is that it can provide a variety of different signatures or tags to that binary once you've uploaded it. So in this case, had I not known what the sample was, I uploaded it to the Malware Bazaar, it could have provided that insight to say, oh, this is actually Formbook. What you're going to find is that Formbook is actually written in native code. And so it's not Formbook itself is not a .NET executable. The .NET executable in this case is actually the program that is used to drop the Formbook payload, the main payload. Now, before we get into looking at the sample, what's also very important to understand is what dnSpy is used for and what it isn't. dnSpy is used, or dnSpyEx is used for looking at .NET executables. Now, we're not going to get into all the details of .NET, but the short version is that .NET executables are written in C# or VB.NET or F#. I think there's a number of supported languages. The original code is then compiled into bytecode, and it's up to the .NET runtime on whatever platform, whatever version of Windows you're executing it on, and other supported platforms actually, in order to convert that bytecode into the machine code during runtime, during execution. What we get then, as a reverse engineer, is we have the ability to look at that bytecode and decompile it rather than disassemble it. That is, we can actually get something that looks closer to C#, that original C#, than having to look at assembly. And that's the main difference between the decompiling and disassembling. Now, the try ID is a way of looking at the file type, and you can see on Malware Bazaar, it doesn't actually provide any insight into the fact that this is a .NET executable. So oftentimes, what I will do is use something like the file utility. In this case, you can see that the file utility provides us with a singular, fairly clear signature. It's saying that this is, in fact, a PE32, a PE, a portable executable file. The main bits here are that it is a mono/.NET assembly. So that's telling us that it's a .NET file. Therefore, it is a good candidate for using dnSpyEx. The other little bit of information here is that it's identified this as a 64-bit file. So the x86-64, that's what represents one way to identify a 64-bit file. So in this case, using file provided us that information, and that can have an impact on a lot of different analysis tools and pipelines that you may work with or develop in the future. What it most impacts today is the fact that we want to use, when you download those dnSpy executables, those release versions to get the tool, you'll get a 32-bit and a 64-bit version. And generally speaking, I'm going to use the version of dnSpy, and I'm just going to say dnSpy. That I'm talking about dnSpyEx. But I'll just say dnSpy for short. So you want to use the version of dnSpy that corresponds to the architecture of whatever you're analyzing. So I have a 64-bit sample here. So I want to use the 64-bit version of dnSpy. Now, dnSpy by default will have three primary windows, as you can see here. The left-hand side will be the Assembly Explorer. Will give us the ability to explore the target executable that we're uploading. Basically, it'll show us that executable as a project, the different classes, the different methods, and that's where we'll begin to unravel the functionality to figure out what it's doing, what it's up to. The main screen in the center is just giving us insight into the code that we're looking at, the specific class, different methods, different resources. In this case, the overview of the project, I just happen to be on dnSpy itself. Below that, I have two tabs open, locals and modules. The modules tab isn't open by default. I'll show you where I open that here once we get into a little bit further into the demonstration. And then the locals tab will be an important one because that will show, particularly if we're debugging, it'll show the value, all of the local variables and then their values. So those are the three main windows. Certainly not all of the windows, but three main windows that are available for you, really right off the bat. Now, once we're ready, we can take our sample and then just simply drag and drop that sample into .dnSpy. And you'll see that now it has been added to the Assembly Explorer. We have, in this case, a very nonsensical name for this particular executable, GHX, so somewhat of a repeating pattern there. And you'll notice off to the right that there is some information about this particular file. One of the things that'll stand out is the comments up above. There's an entry point value, and you'll see all of these /u and then 4 hexadecimal characters or hexadecimal digits. And that indicates that it has a Unicode, it's using Unicode characters for the name of its classes as well as any properties and methods below. If you expand our project, I'll just move this over a little bit, you'll see that also is the case as we start to look at the actual class structure. And so that can be kind of annoying, to say the least. It is a form of obfuscation that is used just to make our analysis a little bit more difficult. One way around that is to use a utility called de4. Unfortunately, this is another project that's been archived. You can still find the project on GitHub. And the VM that I just switched to is actually Remnix, REMNUX. And Remnix still ships with de4 available through the command line. So, using Remnix makes it pretty easy to just simply come in here and go ahead and use it right away from the command line. What we need for de4 in order to work for this example, for this demonstration today, is you provide the input file. I just called the sample formbook.bin. The extension is irrelevant. I typically use .bin extensions just so I don't accidentally double click if it were .exe and I'm analyzing in Windows, which, since this is Windows-based malware, I'm oftentimes in a Windows VM for my analysis. So I don't accidentally double click it and infect myself and then have to deal with sort of the resetting of the VM in order to clean up that accidental infection. The -o argument provides a way to name the output file, and now we can run our de4 tool. And with any luck, you'll see that we'll have an output file now of the name that we desired there via that -o flag. Keep in mind, just calculating the SHA-sum on the original sample and the output, it did modify it. Of course, it had to go in, de4 as a utility went in and change the naming to kind of de-obfuscate that, to not use those Unicode characters, which will now change the file hash. Depending on the type of obfuscation that de4 is dealing with, it may be more invasive in terms of how it changed that target binary. And so sometimes the resulting output file won't execute. And so I usually keep both on hand. And if I have issues with anything that I've tried to de-obfuscate through de4. Maybe let's say we're going to do some dynamic analysis, which we will here, then I'll use the original sort of obfuscated sample for dynamic analysis, but I'll use the cleaned version for that static analysis. Here you can see 2 different hashes. We know that they were modified, but we do know at the same time that they were the same file. Okay, if we go back to our Windows VM, we can now copy that cleaned version in and drop it into dnSpy. Since there is the original sort of obfuscated version, I don't want to get confused between the two. So I'm going to go ahead, right-click on that assembly and remove it. And that will just leave our cleaned version. You can see when we highlight that, for example, the entry point value up above is class5.main. And you're going to see things like class 5, class 4, class 3, different S method underscore, and then a numeric value. And those are just artifacts of de4 sort of cleaning up some of that obfuscation from before. Now, another interesting aspect for this file as we begin to explore is if we look at this particular tab here, what this is telling us is that this module confused by confuser.core, this can sometimes give you insight into the type of obfuscator or packer that was used. In this case, confuser.ex is in fact a well-known obfuscator, and you can look it up on GitHub, or I'm sorry, on a search engine, you'll find it on GitHub, and you'll see with a lot of .NET malware that confuser.ex is certainly used as at least one layer of obfuscation. Now, the goal here isn't to necessarily get into all the ins and outs of confuser.ex. It's definitely something that you want to be aware of if you're going to be looking at .NET malware, because it's quite prevalent. But again, we're not going to get into all the details as to how to automate the defeating of confuser.ex. We'll talk about how it works. You'll definitely be able to recognize it after this video, and then how to sort of work around it quickly. And that's really the goal with a lot of the analysis, at least for this demonstration, is we don't want to get lost in the weeds of anything. We just really want to kind of, how quickly can we go from the beginning sort of unknown state that we're in here to what is the ultimate end state, which is the execution of the Formbook malware, that main payload. Okay, so other things to consider. If you don't have a specific reason or location to begin your analysis, then I typically suggest going to the entry point. And one way to do that is to simply right-click and then select, go to entry point. So dnSpy makes that very easy. In this case, it is main, although I want to point out that there is oftentimes a lot of utilization of constructors. Classes will be instantiated and code will be added to those constructors as a way to continue or even begin execution. And we'll talk a little bit about that when we move into the dynamic analysis phase here. But just something again to keep in mind. Now from main, this is right off the bat where you're going to recognize the confuser.ex code. You'll notice that there are a couple of for loops. This is just a way to sort of indefinitely enter into this switch statement with multiple cases. And what this technique, this confuser is primarily doing is called code flattening. And it's taking the control flow of the program and making it less predictable, making it a little bit flatter. Like if we were to disassemble this using IDAPRO, which you could, you would see the flow graph would become very flat because it would be a switch with multiple cases. Now, what order those cases are executed in is absolutely critical because that's the flow of the program as it needs to execute. But what we can't generally see just by staring at this code is what is that order? Do I know is it case 3, then case 0, then case 1? Or is it case 4, then case 1, then case 0, then case 3? Right? We don't necessarily know that just by looking at it. You'll notice in the switch statement, num2, that is a value that is then used to drive the state of this particular switch. And you'll find, num2 or num, and you'll find that in pretty much all of the case statements, in fact, I believe all of them, Num is at some point assigned a value, usually at the end of the case statement, in order to determine what is the next case statement to go and execute. Some of the case statements will have code that is important. Some of them will simply be there to drive the state to the next. What is that next case that needs to be executed? So that is really kind of the crux of what Confuser EX is doing. At least this is probably the most prominent thing that you'll be able to recognize, and then you'll have to figure out a way to deal with it. For this demonstration, I think the easiest way to do that is, fortunately, the code remains somewhat readable. When analyzing, we want to look for strings. We want to look for key, objects or methods that are being called. For example, at line 45, we have assembly.load. That loads another PE file, another .NET file. So that would make sense that this particular, like at this stage of this dropper, that what it's doing is it has another PE file obfuscated somewhere within its structure, and it's going to deobfuscate that, load it into memory, and execute it. So this is likely a good place for our analysis to pick up. When I start to identify these, if I'm trying to just get through the program and not have to spend a lot of time figuring out how everything works, then what I'll do is I'll set a breakpoint and transition to dynamic analysis. That way I can just see the results of what assembly was loaded rather than having to trace it statically. So that's usually my go-to. I'm usually working in sort of this hybrid mode of static and dynamic analysis. And again, the point is I don't want to necessarily get lost in all the weeds of how everything works, because that's not really important to me at this point in time. Other things to investigate. Well, anytime I see from base64 string, right? That's probably, once that is decoded, that is likely something that's important. We'll be able to monitor these local variables using our local windows below. And so some of these arrays, especially arrays that are just byte arrays, those could contain additional PE files, and then that might be the next stage that we're trying to get to. You'll notice that this is assigned the value text4, which is ultimately assigned the value down here. And you can see that there's many methods that are called in order to ultimately assign that value to text4. Now, dnSpy makes it very easy. You can click on any of these methods, and that will navigate you to the appropriate decompiled location, in which case you can begin to investigate and analyze. Some of them will be, again, very straightforward. Some of it will be very convoluted. Some will have not only evidence of Confuser EX and these really annoying flattened switches, but then also the arithmetic and how it's decoding the characters to get that base64 string can become, tedious to say the least. Sometimes it can be quite complex. Is it impossible to figure out? No, because we can trace this logic and we can figure it out, but you don't necessarily want to, or I in this case, I wouldn't want to spend the time, right? So we can set breakpoints if we really wanted to, and simply see what that value is after all of those methods are called. In the case of these switches, we also, by setting these breakpoints, we also get an idea of the flow of the program. We know the order, and we can kind of guess the order, right? We're not going to decode a base64 string until we have a base64 string. So case 7u most likely comes before case 5u, which most likely comes before case 4u, because we can't load an assembly until we have a decoded, deobfuscated PE file in order to do that. The last thing that we might want to take note of is this invoke member. So this uses the assembly object that is created in case 4u and then invokes a member of it, which means that whatever that assembly is, it's going to call a method in that assembly. So likely this is going to be a DLL file, a library, that then it's calling that specific member. So this is another area where we most likely want to set a breakpoint. Now, when we want to transition to dynamic analysis, it's quite straightforward. We click on the Start button, and you get a little prompt here that says, all right, your debug engine, .NET Framework, what's your executable, the path that this thing was located, what's your working directory, wherever you want that to be, and then break at. Now, you have several options here. You can break when the process is created. You can break at the main entry point. You can break on constructors and the entry point as well. So when I'm looking at something where maybe I'm just not 100% sure, then that's my usual go-to. In this case, I'm pretty confident that the breakpoints we've set will be hit, and therefore I don't need to break because I've already set breakpoints that we'll encounter. Again, if you're not 100% sure, you can use some of these just to help, particularly the module constructor and entry point, because there might be a constructor that's being called from an object that's being instantiated that you didn't detect or observe. Okay, once you're ready, again, I'll go back to don't break. We'll go to OK. Because I didn't provide a quote-unquote valid extension, .exe, it's just asking me, am I sure I want to do this? Yes, I am. And now we have not only our locals window has begun to populate, but where we're at in the code is yellow. That is indicating that is the current instruction that will be executed. Now, all of the basic debugging commands show up above. We can click continue to continue execution till the next breakpoint or until the program terminates. We can stop it. We can restart it. And then we have our basic debugging commands. We can step in, step over, and step out. Step in means we'll step into every one of those method calls. Step out means we'll step out of the current method. And then step over means that we'll step over the current instruction, but execute all of the function calls that were there. So I'm going to do that. I want to step over. That way, all of that still executes, but I don't have to take the time to trace in and out of every one of those function calls. If we look at our locals window, you can see text4 now has a base64 string. And we could double click in there and copy that value out if we wanted to manually take it to another tool and decode it. But because of what we talked about earlier, the flow of this program, I'm just going to continue to trace. So we'll continue to step over. You'll see that we now go. You'll notice with this Confuser EX, if you're stepping through it, that sometimes the flow looks like it doesn't quite add up. Like, why did it go to this num statement in case 0u? It doesn't seem like it should have. And now we're in this case 5u. And that's just the way that dnSpy is showing us the decompiled code. It's the correct flow. It just seems a little disconnected or disoriented. But it is in fact the correct flow. So something to keep in mind, obfuscations like this can just really, they can cause some unexpected behaviors. Here we can see, of course, now we're on to our breakpoint where we're going to base64 decode. If you're familiar with PE files that are encoded using base64, you might have already recognized that pattern in that text4 string, the tvpfu. But we can now look at the value of the array. If we want to expand that, it's a large array. You can see the size is 2E400. And if we say yes, go ahead, now we can investigate the first 2 bytes, 4D5A, those are the first 2 hex values for a PE file. So that represents MZ. And that's, again, a pretty strong indication that that is a PE file. So we could right click and save if we wanted to, and that would allow us to save all of the contents of that array. But because we're debugging, we actually can use dnSpy to jump into this what will eventually become a loaded DLL. So let's just continue. Now we're to the point where we have the assembly load instruction. Now, the modules, I said, was opened using debug, Windows, and there is modules. So I don't think that's there by default. That's how I opened it. And you'll see that once we execute that instruction, we now have a new module called bum that is loaded. You can double click on that, and that actually will load that module here in our Assembly Explorer. So now we can explore this as we would any other .NET assembly. Even better than that, we can actually set breakpoints here. So now we can debug this DLL as we're debugging the main executable that we started with. Okay, up here, navigational arrows. So we'll use that to go back. And I'm just going to go ahead and continue because this is where we're calling that invoke member. Text2, let's go back to our locals window. We'll condense that array. And if you look at the value of text2, you see that it is bum run. So looking over at the side here, because this is a DLL, we can't right click and say go to entry point, right? We need to know where the executable that's loading this, what method it's actually calling. And now we know that. We know that it's bum run. So you can see I already had a breakpoint set as I was preparing this demonstration for this recording. And now since we set a breakpoint here, when we, once go back to this here, once we allow this method to execute, it'll catch over in the bum run. So now we're able to kind of continue our dynamic analysis into this extracted DLL, this discovered de-obfuscated DLL. Now, we may not quite know what to do yet, right? We haven't done any static analysis here. But as you can see in this particular method, there's really only one method that is invoked, bum.ce9da, blah, blah, blah. Again, navigation is quite easy. We can click on that and there it is right down here. And now we can begin to analyze much like we did with the previous. What's happening here? Well, you'll notice that there are a couple of other arguments that were passed. First one is the path. And that is a path of an existing executable that is likely going to be already available in Windows, regsvcs.exe. And what this ultimately is doing is it's going to perform process hallowing on that target executable. So it's going to load that regsvcs.exe in a suspended state. It's going to then remove the code there, inject new code, and then begin the execution. And it's that injected payload, that replaced code, that is Formbook in this case. How do we know that? Well, if you start to investigate, let's see if this is one. Nope, that's not one. We'll go just a little bit further down. Here we go. If you look at some of the different methods that this particular DLL imports, you'll see we have create process, get thread context, set thread context, read process memory, write process memory, unmap view of section, virtual alloc ex, resume thread. And those are all methods needed in order to perform process hallowing. So what will happen is that the create process will be called, then get thread context will get the initial thread context. That's information about the registers of that process. It's needed so that once the new code is injected, the entry point can be updated and a call to set thread context can be made. From there, virtual alloc ex allows a program to allocate memory in another process. So we have our newly spawned but suspended process that the current process we're in will allocate new memory in. The unmap view of section removes the code of the existing suspended process. Write process memory allows us then to, or allows this program to inject the new malware in, and then resume thread allows that thread to begin execution. And the whole reason it does that is so that it looks like, upon investigation, that this is the path that was loaded of that process, that it's a legitimate executable, but in fact, it's not. So, there's a number of different APIs here that we could focus in on, but I like write process memory because that, if we, look at that one, then that is likely when our PE file, our final payload, has been, de-obfuscated and placed into memory of the suspended process. So I'm just going to copy that value for this method. I'm going to go back to this this screen, the series of function calls that we're now that we're going to enter in just a minute. And I'm just going to search for it. And let's see. There is an instance, and there is an instance. So now what I can do, maybe just set a few breakpoints here. There's a breakpoint. And let's set a breakpoint here. That way, I don't have to necessarily trace all of the logic of what's going on here. I can set these breakpoints, allow the program to run, and then investigate what's happening to see if I can find that next stage PE file in memory to extract it. Does this method always work? No, it doesn't always work. This is sometimes trial and error, but this is usually the first thing that I do try, just so that, again, I don't have to get lost in all of the details in getting to that next stage. Okay, we'll go back, and if we sort of kind of lose our place, you can navigate forwards and backwards, or I can just step into, and that'll take us to the location where we last left off, because we're currently debugging. So now we can step into this method, and because I have those breakpoints set, again, you could certainly continue to single step, but I'm just going to select continue. I set some breakpoints from earlier, again, before the demo, so I just forgot to clear those. That one's not important right now. Let's see. So there we have it. We have our first one, write process memory. Now, if you don't know what a particular API does, so we know that this is eventually going to call write process memory, then you'll have arguments defined here where it was imported. That might not be good enough. So then what we can do is simply look it up on MSDN. And what I'm interested in this case is, what is the buffer? That is, what is the content that we're writing? So we can confirm the handle to the process. That can tell us for sure what process we're accessing memory on. We can look at the base address, so we know where in that process the base of the allocation. And then again, in this case, probably the most important is, what is the pointer to the buffer for the content that is going to be written into that location? Because in this case, if it's our PE file, then that's where that PE file is going to live. Whoops. So what was that? That was 1, 2, 3, the third argument. If we go back then to our code here, we can count 1, 2, and 3. So CF699, that is the third argument, so that should be our buffer. If we look down below CF699, that's a byte array, fairly large one, another indication that it is in fact a PE file, and we can expand that. And there we have 4D5A, right? So it is a PE file, and that would make sense, kind of lining up with what we anticipated here. I'm going to go ahead and save that so that we can investigate what this next stage is. Okay, after saving that to the file system, I called this formbook.stage3.bin. This is the, in my mind, this is the third PE file to, including the original that we started with that we've now encountered. We don't know what it is. This could be another assembly. This could be another stage. Even though we've seen very clear evidence of process hollowing, that doesn't mean that it's not another .NET file. But if we run the file command on it, you can see that it is not. It is a PE32 executable, and it is not, there's no indication here that it is a .NET file. So we can't use dnSpy for our continued analysis. Now, usually at this point, one of the first things I want to figure out is this a valid file? So we can use get file hash and, stage3.bin. I'm just using a little PowerShell to get our SHA 256, and we can go to triage. As you can see, I've already looked this up, but paste that in again. There's the file. Yes, I uploaded that earlier. And here you can see now, here is, we know that we've got a valid extraction, that we've got our file. Not only did a place like Triage, an online sandbox, identify it with its tags as Formbook, But when you look at the two tabs to the right, those are the dynamic analysis results. It was able to execute this as well. So we know that our extraction is essentially clean. There's no further obfuscation or anything that well, let me rephrase that. We have a valid PE file. If we were to now analyze this PE file, yes, we're going to deal with more obfuscation. There could be another layer of packing, but we've moved from the .NET component of it to now this native code. And so we'd have to use a tool like IDAPRO or Ghidra. We'd have to use a different debugger, something like X32debug or WinDebug or something that can handle those file types. So different file type, dnSpy is no longer applicable here. All right, so what do we do with dnSpy now? Well, the last thing that will happen here is that it will resume that hollow process, which will then start the execution of our malware. We can't trace the debugging with dnSpy, so we'd have to attach with a different debugger or kind of switch our analysis. But that wasn't the goal. The goal here was just to walk you through how to get started with dnSpy, and this was just a good example because you'll find a lot of malware uses these .NET droppers or even downloaders as sort of the first stage of packing and obfuscation in order to stage and execute that next stage, which could be native code, could be a PE file. Lots of stuff here that we could explore with dnSpy, only scratching the surface, but hopefully this is a good primer to get you started and using it and investigating that .NET malware. So stay tuned. We'll have more videos to come in the future, certainly more around .NET malware. And if you have any feedback, please leave it below. Comments will be open. I look forward to reading those. And until then, take care.